So we're going to define what a homomorphism is in this video, and I'm going to give you a soft definition, that is a non-rigorous definition, a definition that we're not going to use, but it's helpful to understand what the real definition is trying to capture. So if R and S are rings, they're firstly sets, right? They're sets with some extra information. A homomorphism is a function from R to S such that phi preserves ring theoretic stuff. Stuff I'm going to blanket as structure. So namely, rings come equipped with some information. They come equipped with addition, and they come equipped with multiplication, and the addition and multiplication interact somehow. So we don't want to consider all functions from R to S. We want to consider only the ones that sort of make sense in algebra. That is, the ones that preserve the structures that we have. So again, that's not the real definition. That's what the definition that I'm about to write down is going to try to capture. But we should think about ring homomorphisms as structure preserving functions. So what's the actual definition? Okay, well, R and S are rings, arbitrary rings. A function, so it's firstly a function from R to S is called a ring homomorphism. What are we going to use here? Ring homomorphism. Or sometimes just ring hom. It's kind of a long word to say. If the following are true. For all x, y in R, phi of x plus y is phi of x plus phi of y. So we say it preserves addition. Phi of x times y is phi of x times phi of y. So the first property is breaking up under addition or preserving addition. The second property is breaking up under multiplication or preserves multiplication. And we have a third property, which is very important. Phi of 1 needs to be 1. So that's to preserve unity. So that's to send the unity in R to the unity in S. Now, there are a bunch of types of ring homomorphisms, and we're going to do some examples in a second, but I'm going to unload a bunch of language right now. So this is the end of the definition of ring homomorphisms. Further, so if phi from R to S satisfies these properties, so is a ring hom, I'll write it out though. We say phi is A, and there's going to be a bunch of different things here. It's a monomorphism. If it's 1-to-1. It's an epimorphism if it's onto. It's an isomorphism if phi is both a is monomorphic or is a monomorphism and an epimorphism. So it's 1-to-1 and onto. And then it is an automorphism. There's lots of orphisms going on here. if phi is an isomorphism, and S and R are the same thing. So the domain and codomain are the same thing. So it's an isomorphism from R to itself. So mono, mono kind of makes sense, one-to-one. Epimorphism is onto. Isomorphism is our notion of sameness, as we will see. Automorphism is, auto is self, so it's a self similarity. So R and S are the same thing. So there's a lot of language, a lot of different types of homomorphisms. In the next video, we're gonna do a deep dive into language with a lot of examples.